I want to thank everyone for attending today. My name is Tom Tansey. So good morning to all of our friends in Australia, and good evening, I guess, to also in Asia, and good evening to everyone else. And so, as I said, my name is Tom Tansey. I'm with the SunSpec Alliance. I'm going to be your host today for this workshop, where we're going to talk about distributed energy resource networks and the Australian marketplace. And to begin, I want to thank my colleagues that have helped us organize this event in Australia. Many of you, AEMO, a number of the different utilities, nonprofit organizations, and so forth that helped to raise awareness for the program that we have going here and getting the word out. So I want to really send my thanks to you all for doing that. Also want to thank our sponsor, PXiSE Energy Solutions, for their generous financial support to help us put on this particular workshop. So we do a lot of these things, and we can't do it without the support of our members. So thank you again to PXiSE. As we're all quite aware, the entire world is in the midst of an energy transformation where fossil fuels are being replaced by renewables and distributed energy resources such as solar and wind and batteries. And at the same time, every aspect of our society is becoming both electrified and then networked to make all these types of distributed energy resources work in concert with one another. And so taking a leadership position in this area of DER networking is both Australia and my home state of California. These two territories or regions have been at the forefront of this movement to get more distributed and renewable energy onto the grid. And we're learning a heck of a lot about how things work, and also sometimes about how sometimes they don't work so well. And all this stuff is important to us as we develop this new type of energy economy. And so that's why we're here today, to share our stories of success and failure and to learn from each other to get it right. Now, as I was doing some research for this particular workshop, what really struck me is that the premise that we had set up, where Australia can gather some lessons learned from other territories, was really sort of partly right, but a little bit off base. And so what do I mean by that? California and the U.S., but in particular California, I think got in front of this parade as far back as maybe 2012, when we first started to work on what was then known as SEP2, Smart Energy Profile 2, the standard that then became IEEE 2030.5. And we worked to put distributed energy resources modeling and capabilities into that standard at that time. And then a few years later, 2014, I want to say 2015, the California Public Utility Commission sort of went into high gear to get plans in place to change the standards to allow for far more renewables than were allowed by our national regulations at that time. And so from that period of effectively from 2012 on to today, we've had groups that have been convening to work over the different aspects, the technical considerations, the financial considerations, the regulatory considerations, since that whole period of time. We've also done some work to get manufacturers to get their products compliant and then tested and certified. But now, as we arrive here at 2021, this is where the sort of the narrative breaks down about California being out ahead. Because now when it comes to implementation, I would say that Australia and California are about neck and neck, which is kind of interesting. Yeah, and of course, driven by sort of a different need, I think, that we saw in California I mean, I know that you have, and we're going to hear about this, of course, issues with the grid and issues for the need for power and for climate change solutions and so forth that had been sprung upon you, and so you've had to take action. Really had no choice. Whereas in some ways, California had a little bit more luxurious time, if you will, to get the engine revved up. So here we arrived together, and we've done all this prep work, and now we're starting to roll out these systems into the field. And so we're going to learn a lot from each other, I think, in this workshop. So one of the topics that we'll cover today is this data communication standard called IEEE 2030.5. And we're also going to focus in on a topic called the Common Smart Inverter Profile for Australia, also known as CSIP-Oz, as I was mentioning. So networks are a key ingredient for this system to unlock the value. And this idea of a common profile, which was put forth in California, is I think I mentioned, we developed the Common Smart Inverter Profile back in 2018 initially. But now when you apply it to the Australian market, you have slightly different concerns. For example, concerns about export limitations and so forth that maybe weren't considered. So some adaptations were needed. And so, as of August of this year, the CSIP-Oz is now available. So we're going to be talking about that today as well. So with that as sort of the preamble and the setup for today's session, we have an agenda that is comprised of 4 main parts. First, we'll start off with an IEEE 2030.5 case study. Now, this will be presented by our colleague, Chuck Wells. So, Chuck, have you checked in?
Yeah, I'm here. Can you hear me?
Excellent. Yeah, loud and clear, right? So we'll have Chuck kick off the event, and we'll go for about 15 minutes describing how 2030.5 has been applied in the Onslow power station. And from there, that'll be a good jumping off point for us now that we would have introduced what the 2030.5 network is and what it can do. There we'll pick up our first panel session, which is the Australian Common Smart Inverter Profile, also known as CSIP in the vernacular. And again, we're going to compare notes about what we learned from the process of the US and how that's now being applied and adapted in Australia. And for that session, we have as our panelist Ben Ealey. He's the program lead of Information and Communication Technologies for TERs at Electric Power Research, also known as EPRI. We also have Dr. Robby Simpson. He is the chairman of the IEEE 2030.5 standard and has been for working on this committee for some time, has participated in the last couple of iterations and drafts of that standard. And so I have the pleasure of working with him on that committee. So Robby is a system architect at GE, and as I mentioned, also the technical chair for the 2035 standard. And finally, when our panel is rounded out by a person who is one of the principal authors of CSIP-Oz, Ben Weise, lead developer of battery storage and grid integration program at the Australia National University, the College of Engineering and Science. So I think a pretty good, well-balanced panel there. And so that will take us into about an hour 10 into the program. Then we're going to do a 5-minute bio break, which we'll do between each of the panels. And so as this is a virtual conference, there's no mingling in the hallways, unfortunately, but we'll be able to take a bio break. And then when we come back, our second panel is going to deal with DER standards and governance in Australia. And again, this is a set lessons learned in terms of setting up these types of systems that work for everyone. And this one, again, I think is it's a bit of a challenging topic because we utilize, every country effectively utilizes international standards. And then we have to make them work in our home turf. And so that's no mean feat of socializing the issues and getting all of the right parties in place such that the manufacturers and the integrators and the network operators and the utilities and whoever else needs to be involved in the overall delivery chain feels like their needs are being addressed, then the requirements are being met, and it's an easy enough process that we can keep in an open market. And so that's a heck of a challenge. And so for this panel, we have Rod Adur, who's a solutions manager from Fronius Australia, Darren Gladman, and he's the director of the Clean Energy Council of Australia, and then Chuck Wells, who will be giving our first presentation with PXiSE, will round out that particular panel. We'll take another 5 minutes after that, and then finally we'll close the session with the discussion of cybersecurity. And in particular, we're going to dive into issues associated with public key infrastructure. Over-the-wire security, I think, is one of the first places people start in this business in terms of applying security policy. And so that's where we'll start as well. Now, public key infrastructure, cybersecurity in general, obviously this is a global challenge for every sovereign nation. And here, one of the topics we're going to discuss is, what about the PKI for Australia? And what about planning the root authority on sovereign Australian soil? And so again, this is a topic that seems to be very timely, coming up in territory after territory. And so we have our experts here, Dave Bradshaw. He's an enterprise security architect at AEMO. We'll have Jay Johnson also. He is a principal member of the technical staff at Sandia National Laboratories and has been working in terms of developing smart inverters and cybersecurity practices globally in his position with Sandia National Labs in Albuquerque, New Mexico. We also have Dr. Massimiliano Pala. I know him as Max. And so Max is the director of PK architectures at Cable Labs and also works in quantum computing with OpenCA Labs. Max helped the SunSpec Alliance set up our public key infrastructure for IEEE 2030.5 and helped us devise our security and certificate policy. And then finally, Dr. Helga Janeka, who's a research director of Australia's Cybersecurity Collaboration Center, and he's going to let us know about all the plans that Australia has in mind for how to apply this technology. So our intention, and hopefully we've achieved it, is to get some balance on this, make it kind of a 50-50 deal, half Australians and half people from other parts of the world, so we can have a good cultural interchange. Again, the point is to learn from each other, see what we can do here. All right, I've been going on for a while, so I'm about to stop. But before I do, I want to introduce my company, the SunSpec Alliance. We are a nonprofit organization, and we're global in nature. We have about 140 companies that participate with us. A third are from Asia, Asia Pacific, and a third are from Europe, and a third are from the US. And so we have a really nice balance. We have many different manufacturers, and of course, the other parts of the ecosystem that deploy these resources in territories all over the world. Our specialty is as a standards developer and a testing and certification authority. So the standards that we develop are all pertaining to distributed energy resource data communications. The SunSpec Modbus standard is our flagship. It's now part of the US, the Danish, and the Polish national standards, in Canada as well. And so it's built in fundamentally to how the inverters work. We also offer testing and certification for IEEE 2030.5 and have done a lot of work in that arena. So that's about the SunSpec Alliance, and we're here for the common good and also to spread the word about distributed energy, grow the market. All right, so that's the quick intro. Maybe not so quick, but it's the intro. And so now I'm going to And with that, I want to introduce Dr. Chuck Wells. He's the Chief Technology Architect and co-inventor, PXiSE Energy Solutions, who's going to tell us about his work that he's done in Onslow. Chuck, over to you.
Okay, well, thank you very much, Tom. I hope you guys can hear me well. What I'd like to start out with is some of the potential applications of the technology, of the protocol technology in power systems. I think, go ahead to the next slide. So there's quite a number of potential applications of the technology. Many of these are actually outlined in the specifications itself, but there's some other applications that can be used using the functions of the standard. In particular, there's a function called the meter mirror, which allows a server to collect data from clients of any type at any rate. And this information can be used to apply direct controls to the grid through the DERs. One of the big advantages we see of the technology is its ability to communicate securely over the internet. In the third session today, we'll hear more about that technology. It also provides the opportunity to allow DERs to participate in markets. There's specific functions in the standard that allow for direct participation by aggregators into the market as well as individual DERs. Additionally, if you have the ability to read data from the DERs, this provides an opportunity for utilities to offer more direct control of the distribution system. In particular, voltage regulation is possible. In fact, autonomous voltage regulation is supported by the standard. Conservation voltage reduction technology can also be applied. Again, this is through the use of the meter mirror to provide data from the local facility to the server that can calculate what the control function should be and then issue real and reactive power commands back to the DERs. The same applies to thermal power management. We see in many cases, in particular Onslow is one as well, where we have to be aware when we make a dispatch to a DER that we don't cause an exceedance in the amperage capability of the lines that are connected to that DER. Frequency control is another very important capability of the protocol. This is going to be quite important, we believe, in places like South Australia, which is currently encountering some issues with system inertia, loss of system inertia. And that leads to the use of these DERs to increase the stability of the power grid. So a couple of other functions that we believe can be used quite easily, and that is to provide closed-loop control of the DERs on grids that have very low or zero spinning inertia. This is already in South Inertia, where we read in the latest issue of the IEEE Power and Energy magazine that at times South Australia has 150% inverter-based power injection into the grid. And of course, the technology specifically allows dispatch into microgrids to provide ancillary services to the distribution. So let's go next to a typical example. This is in Australia, in Western Australia. Our company has been working on this for 2 years. It's currently been in operation for 1 year. If we go on to the next slide, I'll give you an example of some of the technology that has been implemented here and how it's been implemented using the 2030.5. Onslow, or Horizon Power, was one of the first companies to adopt or to mandate the use of 2030.5 in this project. This means that from the central server located in Perth, this is the location of the master DERM system. It dispatches commands every 5 minutes to nearly 270 controllable DER devices located 1,400 kilometers away from the central server. Messages are sent over internet. There is a cellular modem attached to each of the customer's devices, but basically the packets travel securely over the internet every 5 minutes to the DERs, and then we send control commands to those devices to make sure that the local network is stable, that it is within voltage constraints, and within thermal constraints. Now, the system also includes control of utility assets, and this is done through a linkage, a SCADA link, a secure SCADA link owned by Horizon Power, so that we can communicate to the utility assets that are located at Onslow. And they're in the next slide, I'll show you what they are. But basically, so there's two methods of communicating. One is to communicate with 2030.5 to the customer DERs. The other is to use the SCADA network to communicate to the utility-controlled assets. And these utility-controlled assets are controlled at a much faster rate than the customer-owned DERs. So there's located also in Perth is a microgrid. It's a PXiSE microgrid system that basically the town power supply is located about 17 kilometers south of the town over a dual transmission line, and that can be considered like the utility. And then there's a connection to the town through switches, and the town becomes the microgrid, so that we have a microgrid and a DERMS controller located in Perth. The slave DERMS is located in the substation, and as I said, the customer DER controls are through Perth. So there are eight fossil generators. There are two batteries, utility owned, and one solar farm owned by the utilities. And I said over 270 customers are receiving messages from Perth over 2030.5 at 5-minute intervals. So let's go to the next slide. This is a typical example of the real-time operator screens. These screens are visible to operators located in Onslow as well as in Perth. It shows a number of variables that, including what the forecasted power is, what the current command power is, what the forecasted solar generation is, and this is the primary screen that is used by the operator. Now, this system also determines how many generators should be running in order to meet the forecasted demand. The goal is to run with zero fossil generated fuels. And if you see on the top trend line, there's a line that shows what is the maximum number of generators that can be run. It's now set to 2. But there are times during the day when the generators can be turned entirely off, and there's a small little rectangle below just below the top trend, and that tells the operators that anytime in that window, the system, all the generators can be turned off, and the system can be run 100% renewable power. And so we've demonstrated that now for several months. It's quite a feat, we believe, to be able to have the system determine when it's safe to go with 100% renewables. No inertia is in the system now. This is a system that's controlled with zero inertia, and it's controlled with the battery, the utility battery, and the customer DERs. Let's go to the next slide. As a result, so far in Oslo, we've calculated that on an annual basis, they can save natural gas consumption of 55,000 gigajoules per year. That eliminates 3,000 metric tons of CO2 annually. The most important thing is we've been able to prove that the town of Onslow can get a threefold increase in the renewable hosting capacity. Prior to this project, there was a limit to the amount of DERs that could be put into the grid. We've increased that by a factor of 3. We've been able to show that we can reduce the communication traffic by 75% over what the initial data consumption was. And as I mentioned, at periods of time during the day, we can run the town with 0 fossil fuel. Let's go to the next slide. Now, this is just a quick summary of some of the things we mentioned already, but you'll notice that one of the major purposes of this standard is to provide the ability for the utility company to manage a number of capabilities of the system. One is it's usable for demand response. It's usable for load control, time of day pricing, distributed generation control, and electric vehicle control. So it has a wide number of uses, and I think that you're going to see in this seminar a number of additional cases discussed. So let's go to the next slide. So the question is, why should we use 2030.5 compared to other approaches? Well, number one, it is a well-developed, very well thought out, approved standard. So when we do implementations of systems that involve with DERs, we don't have to reinvent the wheel. We don't have to build custom messages. We don't have to use custom protocols. We don't have to worry about how we're going to get those messages across the internet. Additionally, it's highly secure. The system uses public key infrastructure with issued certificates to the DERs, and they're also issued to the utility company. All messages are encrypted and decrypted at both ends. Most of the control functions that are needed for utility control are already fully defined in the standard. There are quite a number of market functions that are also included in the standard. So like pricing and tariffs are already included. Additionally, the standard can be extended to meet specific needs. And it does not require any custom hardware. The inverter itself can be connected directly to a homeowner's router and communicate to the server over the existing router and the internet. Now, an additional reason to use it is that all DER systems in California are required to use this protocol starting next summer. Previously, several years ago, the initial date was the summer of 2020, but it's slipped a few years. So, and anyway, all DER systems are required to use this protocol. So that's a pretty good reason to use the protocol. Let's go to the next slide. As I mentioned earlier, this has a very rich set of built-in functions. So we don't have to reinvent anything. We simply have to use the standard functions that are included in the system. Now, in the standard, if you read it carefully, you'll see there's really no defined standard of what the time interval should be. Several of the examples about sending messages every 15 minutes is an example. But at Oslo, we chose to run the controls every 5 minutes. But there's nothing to prevent us from running that protocol in 4-second intervals or even faster. The protocol includes the ability to communicate with aggregators, which we believe will be very common in the future, where there'll be commercial aggregators that are participating in the market. Those functions are fully defined. There is a rich set of control commands. We're going to talk about a few of them that allow dispatch to for ancillary services markets like essential system services, for example, is a good example. It supports demand response load control. It supports voltage control. It supports group control. And what this means is that through the protocol, the server can send a droop curve to the device, tell the device to go on droop control with these settings for this amount of period. And this amount of period can be an infinitely long period or it can be 5 minutes. So say, go on droop control with this setting for 5 minutes. It's a pretty robust way to define controls for these DERs. So let's go to the next slide. This is a typical example of what they call an energy resources function set. And I just want to take a minute to describe the chart on the right. Many companies do have issues with, you know, the SIGN, the sign of power. Is positive power going into the DER or is it coming out of the DER? The same way with reactive power. So this is a standard where the 4-quadrant inverter is defined specifically in this standard. So there's no confusion about when I send a command of real power to the inverter, is it to absorb power or is it to generate power? It's very clear from this standard. And of course, this covers a large number of potential applications, including fuel cells, inverters, backup generation units, storage systems, electric vehicles, including home energy systems. Let's go to the next slide, which is this is something that is also important in the standard. Is it clearly defines the difference between how you communicate to an aggregator and how do you communicate to a facility. So there's two different types of devices that we can communicate to. One of them is a single facility that may have many devices underneath it, but is only required to provide information about its point of interconnection to the grid. And then there's an aggregator, where an aggregator has multiple DERs underneath it, and it is responsible to report not only what the total is at the point of interconnection, but also to report the properties of all the DERs that it controls. So that is a very good function to use for controlling signals to aggregators. So that basically concludes the brief introduction to our view of how this protocol can be used in controlling distributed energy functions in the grid. And it's rich enough so that it really doesn't have to be limited to a distribution system. It can be used to transmit any real-time data from any device on the internet back to 2030.5 server.
Well, great. Thank you, Chuck. I really appreciate that. Now, with regard to the questions, we have quite a lot of them piled up here. And some of them I think I may well save until the second panel when you're back up on the stage again. But I did want to just maybe cover a couple of them. One is that David Coots says that controlling 270 DERs with a hierarchical command and control standard like 23.5 is very tractable. But what about if you increase the number of devices to greater than 100,000? You know, smartphone networks can manage millions of devices, but take quite a different approach.
Yes, that's an extremely good question. And we believe that the best way to handle the scalability is to do it through connected microgrids. So the protocol should be able to send commands. It can send commands to any device. But let's suppose you set up a microgrid like we did at Onslow. You know, Onslow only has about 1,000 people, but basically it is a microgrid. So our view is to scale. You do hierarchical control of microgrids, and the protocol is used to send commands to microgrids. The microgrid, and then in turn, then will allocate power flows to the DERs within the microgrid. That's our approach to scalability through hierarchical control of clusters of microgrids.
Right. Absolutely. Another approach is, of course, is through aggregation, which we're going to cover in the very next topic, which has to do with CSIP and the CSIP from California as well. So, Chuck, thank you so much for those great remarks. I think you did a great job of setting up the conversation. And so I think we're going to make a quick shift change here. And so then we're going to bring on Robby Simpson, Ben Weise, and Ben Ealey. Chuck, thanks again for your help here.
Okay, thank you very much, Tom.
Great, appreciate it. Okay, so the next topic we are going to cover is the Australian Common Smart Inverter Profile for the IEEE 2030.5 protocol. And so what can we learn from each other? So here, what I'd like to do is offer our panelists the opportunity to make some introductory statements about this. And so I'm going to call on Robby Simpson first to lead off here, to reflect on what you heard from Chuck in terms of the introduction. How well did he do it in framing it up? A question I have is about on aggregation front. So aggregation is sort of not a completely defined role, but that's where CSIP comes in. So Robby, why don't we start with you, and then we'll move on.
Sure, thanks, Tom. So first off, thanks, Chuck. That was an excellent presentation, an excellent kickoff, and I am probably, like many others, thrilled to see a lot of the good work that's going on in Onslow. It's fantastic to see an area that can be run with 100% renewables. It really makes all the effort that everyone has put into 2030.5 quite worth it. In terms of kind of this panel and how we can best work together and that sort of thing, I think, well, first off, a workshop like this, and thanks for organizing this, Tom, is a great step. And I think the adoption of a global standard like IEEE 2030.5 is the crucial aspect. And I think everyone here gets that, and so we're off to I wouldn't even say a great start. We're off running very well. You know, my experience personally has been a lot with a lot of the activities that have gone on in California with the Common Smart Inverter Profile that was created there. And I think one thing that California really did well, and I see that happening in Australia as well, is that California worked really hard to have all of the right people or all of the right stakeholders at the table. So you had the regulators were involved in a lot of these discussions. People from the CPUC, the California Public Utility Commission, and involved directly in the writing of California's Rule 21 and kind of getting their hands dirty, if you will, with understanding interoperability and why standards are important. Of course, you had vendors at the table because the vendors are very much going to be impacted by the requirements. Likewise, you had the utilities at the table. And then you had representatives from the standards bodies themselves. And so I think what's really worked well in California and what I see going on in Australia also is having all of these folks at the table and working well to put requirements in place and to shape a profile that will work for everyone. And the more that we can all work together and use similar profiles, if not identical profiles, and identical standards, I think the better off we'll be because you'll start to get the economies of scale. You won't have products that have to be built for different regions. And frankly, you'll also be able to take advantage of the fact that of the fact that a lot of these devices, unlike what is typical in kind of the utility or power world, a lot of these devices are going to be owned by consumers and are going to be available in the retail market. So you can get on eBay and you can buy a solar inverter. And I don't know that it would be a good idea for the typical user to have to get on eBay and buy a solar inverter, specifically for the state of California or specifically for the state of or the country of Australia. So, as we can have more commonality and use these standards, I think we enable that retail market and we enable that those economies of scale. So yeah, that's kind of my thinking up front, Colin. Thank you.
Great, appreciate that, Robby. Ben, next I'll go to you. And so you have been one of the principals in terms of developing the Australian CSIP. Tell us about your motivations. Yeah, why didn't the CSIP that existed work for Australia?
Yeah, thanks, Tom, and thanks for the invite to participate in this. So the working group I'm involved in, we kind of formed in 2019 as really at the time just kind of a more organic collection of organisations that were involved in projects around the kind of just the coordination and management of distributed DER. And so the use cases we were looking at were really focused on that. Like I guess our kind of reason for being is that we wanted to make the best use of the most distributed DER that the network can support, and we wanted to figure out what we needed to do to help support that. And so it was really a kind of use case focused that brought us together. Since then, obviously, the group has expanded, and we've kind of ended up producing this CSIP Australian document. There are a few kind of principles that went into this. So we were initially just looking more generally at the types of standards that could support this type of communication, and early on kind of settled on 20.3.5 as the most feasible path forward for the use cases that we were looking at. But we wanted to make sure that we were kind of looking at this as a process that we can repeat across networks. So we wanted to make sure that we didn't kind of do custom integrations for particular projects that, when scaled out, were no longer kind of useful and couldn't be used across projects. Wanted to make sure that we were maintaining or lowering barriers to entry for participants. So not sure exactly what it's like in California, but in Australia we have, I think as was mentioned before, we have a number of kind of smaller startup types in aggregator roles, in manufacturer roles. You want to make sure that everyone can kind of access these potential markets equally, and wanted to make sure that it was ready for kind of future technology rollout. So in our group we also have, while we're kind of the initial use cases were focused on the integration of solar, you look at states like South Australia and Queensland that have greater than 40% penetration of household solar. So those are the kind of technical problems in the management of that are really coming to the fore in the very short term. But we're also looking at this in terms of future technologies, so things like electric vehicles, but also things like smart hot water controllers. We have things that aren't just inverter based energy management systems, and we want to cater to those as well. So I guess the principal reasons why we kind of took the CSIP and modified it to our purposes are particularly that use case focus. So we're looking at the dynamic management of imports and exports, and we felt that we needed particular emphasis on that. And out of the CSIP Australia process, we kind of ended up with a set of manufacturer extensions that we think really made sure that that was an unambiguous use case that we can support within CSIP Oz. We also kind of created this document as a way to provide a basis for further work. So I understand that rolling this out across a network, we're going to need additional testing procedures, integration with other standards. So how those testing procedures might relate to existing AS4777 testing procedures and things like that. So we wanted to kind of use this as a basis for the development of those procedures. Comparing to CSIP, there's also parts of CSIP that aren't relevant for Australia. So particularly things that relate to autonomous functions and around 1547. But the way that we've kind of written CSIP Oz is that because it's structured as deltas changes to CSIP, it kind of requires at the moment, having CSIP side by side, but it makes it clear where we're kind of differentiating in terms of our implementations. And then as an Australian document, I think this provides kind of also tools for, for regulation that then supports the larger scale implementation that we're looking at in Australia. So, these are, as I mentioned before, like, the management of, there's a really interesting talk by Chuck there around the management of, of DER for a microgrid. We're starting to see the same kind of things where, South Australia has hit 100% renewable generation and higher, huge amounts of distributed DER. We're kind of looking to do the same things, but at the scale of an entire network, not just a microgrid. And so, for those reasons, we've really looked at kind of developing our own kind of understanding and application and implementation of 2030 as a CSIP Australia document.
To follow up on that, Ben Weise, so what are the other alternatives for the Australian market besides IEEE 23.5 for networking DERs?
Yeah, so actually this was kind of a discussion that happened before I even became part of this group, but we were kind of considering other standards protocols like OpenADR for other types of use cases, potentially kind of slightly larger scale systems. There's also kind of discussions around the utility of things like DNP3 for probably not for household use cases, but for more of the kind of commercial, industrial, slightly larger, non-scheduled generation. There'd be things like that were looked at as well.
Got it. Well, it makes sense. Well, it sounds like we the two countries here, or at least the two states, right? The California can't speak for the rest of the U.S., but at least California, it seems to us that Australia is on sort of a similar path, and that we offer different alternatives for how you might network your systems, as I think was noted in the chat. IEEE 1547, which is your functional equivalent of the 4777 standard, but that 1547 standard allows for 3 different communication protocols. Now, as it turns out, these protocols that were in 1547, they serve different purposes. SunSpec Modbus works on the equipment for local plant equipment. DNP3, very popular for substation automation. And then IEEE 23.5 seems to hit that sweet spot for DER system to grid operator integration. And so that's what California has sort of picked out as that's going to be the default for the vast majority of their systems is 23.5 for that reason that Robby mentioned, that you have a lot of copper-sided equipment, obviously, and you need a way to communicate at scale.
And so one thing, just looking at the comments here, one thing I also wanted to kind of have to mention is that for these use cases, for us, we're really, networks particularly are not concerned about what happens beyond the connection point. So the fact that you might have DR in a battery system, an electric vehicle, it's not the control of individual devices that we care about, or me kind of speaking on behalf of the group here. What we're really concerned about, what we're really looking for is that kind of connection point level dynamic management. So not so much looking at, curtailing a particular solar system, but whatever operations are required to kind of keep export limits within certain parameters.
Right. Very good. All right, Mr. Ealey, Ben Ealey, we get the two Ben panel. So in your role, you're advising utilities all over the world about DER integration. And so based upon what you've heard so far, what's your reaction to the approach that's been taken in these two different territories?
The approach sounds good. One of the things that Robby said before that really resonated with me is making sure you have all the right people in the room. When we talk about technical interoperability, a lot of it is just about making sure everyone has the same general understanding of what the system is supposed to be doing. Right. One of the things I've noticed, so Tom, you and I were working on I remember a project for California, I think it may have been 5 or 6 years ago, on some of the first smart inverters in the US that used open standards to implement some of these smart inverter capabilities. And one of the things I've seen since then is that it's important to look at not only how the communication protocol is implemented, but also looking at the device, making sure the device actually behaves in the way that you want it to. It's something I've seen many times in our lab as we've been doing testing on some of these DER systems before they go out in the field for demonstration and pilots. And there's often sort of a disconnect between the signal they receive and what that system actually does. We've seen in the US, the grid codes have really made a pretty big leap by including in the certification process the signal is sent and you actually validate that the system behaves the way it should. So you send a 2030.5 or SunSpec Modbus signal, and then you make sure that it actually performs the intended action. It's not as big of a deal with like some of the larger scale systems, but when you start getting to some of the smaller scale systems, and I saw in the chat people were talking about having thousands of DERs or hundreds of thousands, it can be a lot more difficult to go back and fix those. You can always send out firmware updates, but validating that everything has been done correctly can quickly become fairly expensive. So that's one of the things that, at least from looking at it from an interoperability perspective, making sure you have the right conversations, documenting some of those requirements and actually validating them can really go a long way. And that's something I think that was done pretty well in some of the US standards and the .1 1547.1 testing procedure.
Right. Yeah. And so Ben Weise, well, first of all, Andrew McConnell comments 4777 is not a direct equivalent. It's an inverter standard versus IEEE 1547, which is all about distributed connection performance and distributed energy. So, and Andrew, whereas I believe that you're correct. If you're an inverter manufacturers view it as a IEEE 1547 as an inverter standard. It gets used in that way too. But now, so that's but hey, I don't want to argue about your standard. You know better than I do. Now, but Ben Weise, about this issue of tying together the signaling system to the functional behavior of the inverter. What sort of provisions, or do you know if there are provisions within the Australian scheme for doing testing in that way, or is that something to be worked on?
Yeah, so that's something that we've identified we need to work on through kind of the remaining few months in this year. There are AS4777 does have testing provisions that probably relate pretty closely to the performance that we expect. So it's probably a matter of tying those AS4777 requirements and testing procedures into the communications testing as well. But yeah, that's something that we're going to be working through kind of in the coming couple of months.
I see. All right. And Ben Weise, again, following up with you, what were some of the principal challenges that you faced in developing CSIP Oz?
Yeah, so I mean, there were probably, it's a good question. I've kind of got to reflect back. It's taken us a while to get to this point where I think, the standard itself being relatively new and being not fully, it's not fully rolled out anywhere yet. So I think we kind of have, some direction we can take from other jurisdictions, but I think in a lot of the cases it was partially just us kind of working through as a kind of working group, and kind of the technical discussions that we have in conjunction with the kind of projects that we were running that are kind of making use of this, really just kind of building that expertise and understanding in the group. So in terms of the kind of technical understanding of the protocol, that was that was kind of a relatively long process, I would say. And then also kind of side by side with that, also then we're very much focused on these use cases, and so there was a lot of discussions around how best to approach those as well, like where the principles that we have for the development of this are things that we want to remain consistent. We want to kind of make sure that we're looking, we're forward looking here. We're not just thinking about what we kind of care about right now, which is, you know, what we care about right now and what certain states care about is just the sheer amount of distributed solar. But we understand that there are going to be challenges, you know, down the track in terms of electric vehicle rollouts and just smarter devices more generally. So kind of keeping those two things on track, and then, you know, really just kind of then trying to kind of bring all this together into a document that we can then kind of use as a basis for future work. It was a, you know, it was a slower process than you know, perhaps you'd like, but I think this you know, this way of bringing together you know, these organizations and our group has grown quite a bit over that 2 years as well, just kind of naturally through people kind of being interested in this. Kind of managing that whole process has been, you know, it's been a challenge, but I'm really happy that we've got to the point we currently are at.
Well, I tell you what, having been on this slog for a decade now, getting anything done in 2 years seems like can be a minor miracle. I think it's because of the different parts of society and different parties that this touches on. So hey, keep with it. I think this is part of the story here, is that you have to stick with it. Robby Simpson, why doesn't IEEE 2030.5 cover these use cases well enough such that we don't need a CSIP, PAS, or CSIP, anything?
That's a great question. I think there's with all standards of this sort, there's the need for flexibility for being able to meet the use cases of other folks, and as well as future use cases that we can't even necessarily foresee. And so you want to have that kind of balance in the base standard, if you will, whereas the profiles like CSIP and CSIP Oz are looking at very specific use cases and how you want to use 2030.5 for those specific use cases. So I think the two kind of work hand in hand. And I don't know that you would want to only have one or the other. If you only had the very specific use case types of profiles, it wouldn't have the flexibility for other areas or for other potential use cases or necessarily. And but then again, if you look at the standard itself, there's just so much that the base standard enables, everything from price communication to electric vehicles to demand response. It's so broad, it helps to have a document you can look at, a profile you can look at and test to for a very specific narrow focus. You mentioned aggregators earlier, Tom, as well as Chuck. And interestingly, the term aggregator, when we first penned 2030.5, the term aggregator wasn't even in use yet, I don't think. And we certainly built the standard in such a way that that we would enable something like that. We jokingly called it an ESI in the cloud or ESI in the sky at that point, referring to the Energy Services Interface. So we were thinking along those lines, but it's much like a lot of standards out there. Once they're published, if you have enough flexibility in the standard and kind of hit that sweet spot, it enables use cases in the future that the authors originally might not have even envisioned.
Yeah, it makes sense. That was a bit of course, a rhetorical question, because yeah, it's all about limiting optionality so that we can actually make things work together. It's a harder problem than what it sounds like. Easy to say, hard to achieve interoperability. Ben Ealey, a question came up for you regarding gateways, and so as we know that at least as of today, IEEE 2030.5 is not very commonly integrated on equipment. And you know, Modbus, I'm happy to say SunSpec Modbus is a very popular option there because it's very simple, and of course the Modbus interface is universal, so easy to layer on information models that make sense and that can pair up. So a couple questions for you. One is that EPRI's indicated the benefits of using gateways as an intermediary, and so what's your take on that technology and that position, and also what can you tell us about what you've learned about protocol-to-protocol interoperability.
Sure. Yeah, happy to. So on gateways, yeah, we think this is going to be an important piece of equipment moving forward. If you think about like smaller scale DER, so not the ones that have like strict telemetry requirements where you're putting an RTU on site, smaller scale like commercial or on a home. These systems may support a number of different communication protocols. One thing we're seeing in the U.S. is that a lot of manufacturers tend to move towards protocols they may already be supporting and be implementing some of those standard information models. Like as Tom mentioned, SunSpec Modbus is fairly prevalent, but it may not be the protocol you want to use on a network. A gateway is a piece of equipment that a utility could roll out to map from whatever standard protocol is used at that DER interface to whatever they want to use. So it could be they already have a DMP or a 61850 SCADA network they want to tie it into. It could also be a technology a third-party aggregator could use in order to connect some of these standardized interfaces to their own head end and be able to offer them in a market. Some of the other things it can help with is you think about these systems that are being installed, that their lifespan could be 10 plus years. Manufacturers are often changing the models they support. They may not support models forever. There may be a changing of companies can even go out of business. So when you think about these DERs that are being installed, as we start to rely on them more for flexibility, there is a need to be able to continue to provide some level of security. So another thing we've been looking at EPRI is some of the security features that this tool can provide, where we may not have to put the requirements on the DER itself initially. It can provide us with intelligence of what that DER is doing. It can help us secure the link between the gateway and the DER itself. So it's a piece of technology. We've been developing a number of different features, working on a reference implementation, and I think we've got a public report out on some of the different capabilities these systems can provide. But the list keeps growing. The more we dig into it, the more that we find out what we could actually implement in these systems. Tom, you'd also asked about communication protocol translation.
Yeah, protocol-to-protocol translation.
Yeah, so one of the, there's a couple parts to this. So when you look at a communication protocol, there are the technical parts, the standards, so the syntax, how it's packaged, how it's transmitted, kind of what makes DMP3 different from a 2030.5, different from a Modbus. And then there's the information parts, the semantic information, the data models that are being actually exchanged over those protocols. I'm going to focus more on the semantics, because there are tools out there for mapping some of the technical elements between it, but I think in this conversation, the information part's probably a little more relevant. So one thing is, with the protocols that are out there today, all the DER-focused protocols, they've all been relatively harmonized through a common mapping to the 61850 7-420 standard, which I believe I saw mentioned in the comments earlier. However, one thing we've seen in the U.S. is with the adoption of local regulations and grid codes that really harmonize some of the business drivers behind these communication protocols, it's helped strengthen that alignment between them. So, for example, the 1547, which is the de facto standard in the U.S. for grid codes, it defines functional behaviors for DERs and some of the parameters that are needed to control and monitor the behavior of that DER. And all of these standards have implemented these features to meet those requirements of that standard. And so because this feature set is something that's going to be common across all the utilities in the U.S., it makes it a lot easier to understand and achieve interoperability, because we have that common set of business drivers behind it. In general, this makes interoperability easier on the grid, because we know that signal A in a standard like 2030.5 is going to give us the same result as a signal 1 in like a SunSpec Modbus. And we've been doing some work at EPRI on developing some of the reference protocol mapping, actually through this gateway project that was called out in the chat. And we still run into cases where a standards group may have taken a slightly different approach in how they actually parameterized a capability of a smart inverter. There's multiple ways to describe the same capability with parameters. However, because they're all sort of rooted in that same business driver, it's almost always possible to actually make that mapping. So if I think about like an Australian spin on it and what you guys are trying to achieve, I think in order to have that same linkage between the different protocols to make mapping easier, having a link to a common business context like a local grid code is going to be important to sort of have that same impact on interoperability. And this very much links back to what Robby was mentioning about getting all the parties involved so that everyone is sort of on the same page on what the meaning is behind that information.
And just on that, Ben, yeah, we've also, because in Australia we have 4755 as a demand response set of functionality as a demand response standard, and so part of the CSIP Australia is also a mapping between the kind of demand response modes as presented by 4755 over a kind of 23.5 protocol. So we've kind of looked at that, and I think we have some people on the line who've been involved in that development process and the mapping process as well. If we wanted to talk further about that.
Yeah, very good. Yeah, and so SunSpec was also a party to some of these early gateway projects as well. And this preceded the IEEE 1547, 2018 standard. So within SunSpec Modbus, we had sort of functionally equivalent functions, but they weren't exactly the same, of course, because they hadn't been invented. And so some of those early mappings were tricky because we're trying to interpret effectively, somebody that may have been mastered a grid code of a particular part of the world, and then we're trying to apply it to a sort of a US or some other context. And it was very tricky. And so I think one of the things that the 1547 standard got right is to set up a common function mapping and common semantics. So I don't know if that's been done in 4777, but if not, I think that is really the key for nailing this other problem that was mentioned, to tying together the communication behavior with actual functional behavior. Very hard to get that done without very precise understanding about semantics there. And again, across protocols, because you typically are going to span two protocols in these types of systems, I would think. All right, very good. Well, we've been going on for about 45 minutes here, so let's see if we can take a couple of questions from the audience. And so Jack Terry asks, as an extension to the previous question, one of the questions we come up against with CSIP Oz development is scope of the 2030.5 end device. To achieve flexible exports outcomes, the CSIP Oz allows for an end device to comprise multiple physical devices. Keen for U.S. thoughts on this approach and future direction. I guess, I'll take the first, sort of crack at this. And the U.S. grid codes now, it was sort of pointing out with the 1547 standard, they feature this whole concept of a DER, distributed energy resource. And so a DER can be comprised of one or many power conversion devices. And so ultimately, when in the California context, when we use this 2030.5 interface, it's to tie up with the DER system that again has one or many of these inverters. And so there is, of course, a local mapping that has to take place from, in most typically, from 23.5 CSIP to SunSpec Modbus to make the individual inverters, behave as one common unit. So that's, I think, one of the main ways that we've gone about it. But either Ben or Robby, other takes on that?
If I could, I'll take a look at it from more of a 2030.5 specific view, which is And I should say I'm speaking for myself, not for the working group. So I have to give that disclaimer. When you think about end device in 2030.5, I tend to think of end device as the thing that's the endpoint of communication. It's the thing with a device identifier, an LFDI in the standard. It's the thing that's the end of the communication, but it may have more than one physical device behind it. So you could envision, say, a single gateway that would be the end device, but behind it, maybe you have both solar and storage. And so I think that's kind of built into the standard in the sense that the end device is more the endpoint of communication. In terms of future direction, we're certainly looking at further expanding on how you can proxy for end devices. So much like CSIP does today, where you have the aggregators and they proxy for other end devices, and also looking at true kind of aggregations where you may have multiple end devices kind of packaged up as a single unit. But those are some things that we're kind of looking at for potential changes in the future, or I shouldn't say changes, for potential additions in the future. But the short answer is, yeah, I've always viewed end device as the endpoint of communication, which may be responsible for multiple physical devices behind it.
Yeah, I'll comment on that one too. So it is an interesting question. I know in the U.S., there have been a couple different ways this is captured. So like, I think we talked a little bit in the chat above, but like in California, there's a specific requirement for talking between a utility and an aggregator. That aggregator may be communicating with multiple devices, end devices, but that endpoint is the aggregator. But there's a completely separate set of requirements for the devices that are actually in the field. And one thing I want to call out there is that one action we took in the U.S. was that even if an aggregator is used, it is important to have a standardized local interface to access those devices, because we don't know how long that service may be offered from that aggregator, or if that company will be able to continue to maintain a connection to those DERs. So as a DER becomes more important to the stability of the grid, we do need some way to access it. That was one thing that was captured in grid codes like 1547, and I believe California is also planning to adopt that, though they're also looking at how to standardize at the aggregation level. And this is actually a trend we've seen in the U.S. and some other areas as well, that the need to have a local access to these devices. The 1547 and Rule 21 are two examples, but in like the demand response area, states like Washington State in the Pacific Northwest have mandated local standardized ports for water heaters using a CTA 2045 standard. Some of the building codes in California require interfaces through like OpenADR, and there's a number of other, I'll just generalize them as they're sort of templates for utility programs require some form of local access, and all of those are trying to just make sure there's a way to communicate with these, even if that aggregator interface may not be there. So one thing I guess I would say from a U.S. perspective is just to consider those a bit differently, because they do have different purposes in the end, and you want to make sure that you have the right level of access at both the cloud level as well as the local level.
Very good. Okay, well, I think we should be wrapping up now. So Ben Weise, would you like to weigh in one last time to anything that you've heard here so far, or some parting thoughts?
Yeah, I mean, I think this has all been really interesting discussion for me. I think we a lot of these discussions kind of need to take place in a couple of different levels. So I think there's the kind of higher level, discussion of principles and approaches that we talk about here. And I think now, as we kind of mature in this, there's also, a greater need for those kind of more technical discussions as well to happen. So kind of progressing those on both levels is really important.
I think that's right. I think if we've learned anything working in these venues around the world is that you have to simultaneously work the policy and the technical issues simultaneously work those issues such that you can converge on a solution that's actually workable technically, that also works economically. That seems to be where the real art is. So I applaud you for starting on this journey, and glad to have a fellow traveler to compare notes and learn from. All right, so thank you so much to our panelists, and this leads us to our first break, and it's currently 20 minutes past the hour, so let's take a 5-minute break and then come back at 25 minutes past the hour. All right, be right back.